Hi everyone. In this pre-lecture we're going to talk about a new class of problems that we haven't encountered before, and those are called scattering problems. So previously we'd had a situation kind of like this, v of x, you've got x. We had maybe some kind of potential, something like this. And we had tried to solve the Schrodinger equation to find out what were the allowed energy levels in potentials like this. And each one of these has some energy eigenfunction, psi1, psi2, psi3. And we'd basically been interested in problems of this type, basically specify the potential, solve the Schrodinger equation to figure out what energy levels are allowed and what are the energy eigenfunctions that for the particles which have those energies. So these are what I would call a bound state problem. Bound states meaning the particle's kind of localized in this potential and we want to know what energies can it have. The type of problem that we're interested in now is sort of turning this on its head. If you have some potential and it's going to have some hill, maybe something like this. And the idea is now that I shoot a particle towards this hill and I want to know what happens when it encounters this. So it's a different class of problems. I'm not interested in knowing what energies are allowed. Basically, I give this particle some energy, so I know the energy. What I want to know is what happens to it when it encounters this. Classically, it's easy to understand what would happen. What would happen classically if I shot it in with some energy? We know that there's a turning point here. So this is going to be my turning point. Classically, we could represent it by like a car or something heading towards this hill. If it had some energy here, which is less than, let's call this V max here. If my energy is less than V max, the particle would travel up the hill, stop at the turning point, and then go back out the other way. And if my energy was bigger than V max, it would just make it over the hill and go out the other side. So classically, if E is less than V max, the car will stop partway up and then turn around and go back out the other way. And of course, if the energy is larger than Vmax, it will make it to the other side. That's what happens classically. Now the question is, what if this is not a cart, but a quantum particle? So let's say some electron, right? We know that in quantum mechanics things are not so simple. So there's a probability that it can actually make it through here. It's called tunneling, and then come out the other side. So what we are interested in knowing is what's the probability that the particle will come back? What's the probability that the particle will make it through? These are the questions that we're interested in scattering problems. We specify the energy, we send it towards something, and we know what's the probability that it's going to be reflected backwards, what's the probability it's going to make it through. So let's talk about some general considerations here. This is going to be my potential, and I'm going to divide it into three regions. So this is going to be region 1. In this region, V of x is equal to 0, and then there's going to be some region over here, and then there's going to be something in the middle here where V is equal to something interesting. Okay? And the details of the problem is going to depend on what the interesting thing is. But I'm going to assume that if I go far enough away from whatever's happening here, that I'm going to get to a region where there's basically no forces, no potential over here, and no forces, no potential over here. And the idea to solve these problems is you try to solve the Schrodinger equation in all of the regions, and then you match the wave functions together. Okay, so what happens in the middle is depend on the particular problem, but let's talk in general about these regions on each side, psi1 and psi3. So V is equal to 0. I've got my time-independent Schrodinger equations minus h bar squared over 2m. Psi1 double prime of x is equal to E psi1 of x. Right? No potential. And you can write this as psi1 double prime of x is equal to minus k squared psi1, where k is defined to be square root of 2me over h bar. And the solutions in general can be written as complex exponentials, a e to the I kx plus b e to the minus I kx. And if you think about it, the same thing would be true in region 3, I would have the same solution. I would just have possibly different coefficients here for these arbitrary constants. So psi 3 would be equal to some different constant, let's call it f e to the I kx, plus g e to the minus I kx. How do I interpret these solutions? If I were to put in the time dependence, let's say psi 1, capital psi 1 of x and t is equal to psi 1 of x times e to the minus I e t over h bar. Sometimes people will write this as psi 1 of x e to the I minus I omega t. Omega is defined to be e divided by h bar. If I write that out here, this should be familiar as a plane wave. This is a plane wave traveling to the right. This is a plane wave traveling to the left. I can put these on this diagram. Basically, I'm going to have some wave traveling to the right, which is a e to the I kx, and then some wave traveling to the left, which is b e to the minus I kx. And I would have the same thing over here. So one of them is traveling to the right, one of them is traveling to the left. These are the general solutions in these regions. Now, typically, what we want to do is to try to interpret this physically. I'm going to assume that I shoot the particle in from the left. So this is going to be the particle that I'm shooting in, called the incident wave. So this thing here is called the incident wave. And then this will be the reflected wave. And how do I interpret what's going on here is that if I shoot the particle in from the left, there's going to be some probability that it's going to make it through. So this is going to be my transmitted wave, right? Some possibility that the particle will make it through. How do I interpret this? This wave which is traveling to the left in region 3 is that it's generally allowed mathematically, but it doesn't have a good physical interpretation. So we're going to discard this because it's unphysical. If I send a particle in from the left, there's some probability it's going to bounce back, some probability it's going to make it through. That's the reflected and transmitted waves. And this we can discard as unphysical. I should say this is region 3. Right? These are wave functions. And I want to make connections to probabilities. We know that probability goes like the wave function squared, modulus squared, right? So we define these things called reflection and transmission coefficients. R is going to be the reflection coefficient. It's going to be b squared modulus b squared over a squared, which is the probability of reflection. And we can also define a transmission coefficient, t, which is going to be f squared modulus f squared over modulus a squared, which is the probability of transmission, basically making it through. Of course, the probabilities have to add to 1, so it must always be the case that r plus t is equal to 1. All right, and so how do we actually solve these kinds of problems? Basically what we have to do is we have to specify the particular potential. We have to solve the potential in this region. We have to match the wave functions together so that everything is continuous, and then we calculate these reflection and transmission coefficients. That tells us what's the probability it's going to tunnel through the barrier, what's the probability that it's going to bounce back. So this is how we set up scattering problems, and now we have to move to particular examples, and we'll do that in class. Thank you all very much for your attention. I hope you found this useful, and I will see you in class, and we'll study some more particular examples of this type.